In this very video, we are going to be looking at photoelectric emission. It's a note on photoelectric emission. Definition, this is the emission. Photoelectric emission is the emission of electrons from the surface of metals when light of sufficient energy falls on it. Take note the point, light of sufficient energy. So until a light that has sufficient energy falls on a metal surface, electrons will not be ejected from the surface of the metal. Okay, we start with work function. Now, work function is the minimum energy required for incident light to eject electron from the surface of the metal. Now, note that below this energy, the electrons cannot be ejected from the surface of a metal. Okay, so work function is denoted by the symbol E naught, which is equal to HF naught, and which is equal to C over lambda, HC over lambda naught. You should know that frequency is usually speed all over lambda naught, but the speed here, the C here, is the speed of light, which has a constant value of 3 times 10 to the power 8. Okay, so your E naught here represents work function, your H represents Planck's constant, your F naught is the threshold frequency, your C is the speed of light, and your lambda naught is the threshold wavelength. Now, so you can see here that the threshold frequency is the minimum energy required, or minimum frequency, not energy now, required to eject electrons from the surface of metals. Okay, so that leads us to a question here. What is the work function of sodium metal if the photoelectric threshold wavelength is 680 nanometers? Okay, so in this question here, we are given the wavelength, and we know that work function is equal to HC over lambda naught. Okay, the value of a H is 6.63 times 10 to the power minus 34. The value of your C is a constant. Speed of light is constant, which is 3 times 10 to the power 8. Then the wavelength is given here 680 nano. You should know that nano actually means 10 to the power minus 9. Okay, so when we multiply that, we get this as our answer. Now the next we are looking at is energy of incident light. Now this is the light that falls, or this is the energy of the light that falls on the surface of a metal, denoted by E equal to HF. Okay, so when light falls on the surface of a metal, the energy of that light is called the energy of incident light. Okay, and E equal to HF. Now F here is the frequency of the incident light. Now I want us to note this. If the energy of incident light is less than the work function, there will be no electron. So once energy of the light is less than the work function, electrons will not be emitted. Electrons will not be ejected from the surface. But once E equal to E naught, once the energy is equal to work function, it will just be enough to eject electron from the surface of the metal. Now, but when the energy is greater than the work function, the ejected electron gains kinetic energy. That means the electrons, the remaining energy, the excess energy, is converted to kinetic energy. The electron gains speed, the electron gains kinetic energy. Now we look at the question here. It says, calculate the energy of photon of frequency 4 times 10 to the power 14 hertz. Sorry, that's the unit for frequency is hertz. So 4 times 10 to the power 14. So here we have our formula, E equal to HF. So the Planck's constant times frequency. This is the Planck's constant, which is a constant. Then this is frequency, and that gives us this value. Okay, so that leads us to another question. Determine the wavelength of a photon of energy 600 electron volts. Now that brings us to the point that energy can be measured in electron volts as well as in joules. Okay, and we see here that 1 electron volt is 1.6 times 10 to the power minus 19. So when we say 600 electron volts, it actually means 600 multiplied by 1.6 times 10 to the power minus 19 if we are to convert that to joules. Okay, so that's the energy that we are asked to find. We are asked to find wavelength, but remember that we say E equal to HC over lambda, and making lambda the subject of formula, we are going to get lambda is equal to HC over E. H is 6.63 times 10 to the power minus 34 as a constant. Your C is 3 times 10 to the power 8. then divided by your energy is 600 times 1.6 times 10 to the power minus 19, which gives us this value 2.072 times 10 to the power minus 9 meters. Okay, so that leads us to energy of electron. Now, when energy of incident light is greater than the work function, the excess energy is converted to kinetic energy according to the expression. So that's why we have this. This is only possible whenever the energy is greater than the work function. In that case, now your E would be equal to E naught plus the excess. The excess is converted to kinetic energy. The electrons gain kinetic energy. Okay, so that is what we have here. And your E is HF, your work function is HF naught, and you have your kinetic energy. Your E can also be written as Hc over lambda, your work function Hc over lambda naught, then your kinetic energy. Okay, so that leads us to energy of electrons, which is the kinetic energy still. Kinetic energy of electron actually has the formula half mv squared, okay, or you say electron volts or EV. Now, your M there stands for mass of electron, which is a constant value, 9.1 times 10 to the power minus 31. The V, small v there, is the velocity of electron. E is the charge of electron, which is also constant. The charge of electron is constant, which is 1.6 times 10 to the power minus 19 coulombs. Coulombs is the unit. Then V naught is the stopping potential, which is the potential required to stop the electrons, from motion. Now, leads us to a question here. It says, determine the maximum kinetic energy, that's the first thing we asked to find here, of photoelectrons ejected from a potassium surface by ultraviolet light of wavelength 200 nanometers. Then we have a second question. What is the stopping potential to stop the emission of electrons? The photoelectric threshold wavelength of potassium is 440. This is the threshold wavelength, and why this is the wavelength of the incident light. Now, if we make kinetic energy the subject of formula, remember we say that Hc over lambda is equal to Hc over lambda naught plus kinetic energy. Now, if we make kinetic energy the subject of the formula, that means this crossing the equal sign, we are going to get exactly this formula here. Okay, so now if we substitute the value for H is 6.63 times 10 to the power minus 34. The value for C is 3 times 10 to the power 8. Then 1 over lambda is 1 over 200 times 10 to the power minus 9. Then the same with 1 over lambda naught, which is 1 over 440 times 10 to the power minus 9. And if you calculate that with your calculator, you're going to get 5.424 times 10 to the power minus 19. Which, if you want to represent, this is in joules, if you want to represent in electron volt, you divide by 1.6 times 10 to the power minus 19. Remember that 1 electron volt is equal to 1.6 times 10 to the power minus 19 joules. Okay, so that's exactly what we did here. We divided this value by 1.6 times 10 to the power minus 19 to give us 3.39 electron volts. So the answer to this question is, for the kinetic energy, is 5.424 times 10 to the power minus 19 joules, or you say 3.39 electron volts. Now, the next question we asked to find here is the stopping potential. Now, if you have your kinetic energy in electron volts, then your stopping potential is not a problem. It is still the same 3.39, but just that the unit here is in volts. That leads us to another question here. It says, with what speed will the fastest photoelectrons be emitted from the surface whose work function is 1 electron volt? The work function is 1 electron volt when the surface is illuminated with light of energy 3 electron volts. Okay, now in this case we are given the work function and we are also given the energy of light. So what we don't know is the energy of electron, but in this question we are asked to find the speed. That's the first thing. What are we asked to find? The speed. Now, kinetic energy based on our formula is equal to E minus E naught. Remember, we say that E is equal to E naught plus kinetic energy. So when you make kinetic energy the subject of the formula, you are going to get E minus E naught, which is exactly what we have here. And your E is 3 electron volts minus 1 electron volt, which gives us 2 electron volts. but we need it in joules if we are to find velocity. Since velocity, the SI unit of velocity is meter per second, so we must convert this electron volt to joules, and to do that we multiply by 1.6 times 10 to the power minus 19. So the answer for kinetic energy is, the value for kinetic energy is 3.2 times 10 to the power minus 19 joules. Okay, now remember we also noted that kinetic energy Ke is equal to half mv squared. Okay, if we make v subject of formula, we are going to get square root of 2Ke divided by m. You can achieve by cross multiplying. First you have 2Ke equal to mv squared, then you can here divide both sides by m. Okay, then you now have your v to be equal to square root of 2Ke divided by m. Now if we substitute our value 2 times, your kinetic energy is 3.2 times 10 to the power minus 9. Then the mass of electron, remember I say, is a constant value, which is 9.1 times 10 to the power minus 31. We are going to get this value 838,627.87 meter per second, which you can also write as 8.39 times 10 to the power 5 meter per second. Thank you very much. But let's note before we close two things. First is that the kinetic energy depends on the electron, the energy or frequency of the incident light. So the kinetic energy of the electrons actually depends on the frequency or energy of light. If the energy is high, the kinetic energy is high. If the energy is low, the kinetic energy is low. And the second thing I like us to note here is that the number of emitted electrons depends on the incident intensity of light. So when the intensity of light is much, more electrons will be emitted. So note that the energy of electron, or the frequency of, the energy of incident light or the frequency of incident light has nothing to do with the number of emitted electrons. It is the intensity of the light that determines the number of emitted electrons. Thank you very much. Please, I like you to do well to subscribe so that you can always get updates on every of my classes online. Thank you very much. I wish you the best.